All right, welcome to this video talking about motion in 2D. So we've done motion in 1D and now we are entering another dimension. So prepare yourselves. So it's actually not too scary because the things we're going to be doing in 2D are really just, we're doing two one-dimensional problems added together. And I think you'll see what I mean in a moment there. All right, so if you remember, position is a vector that can include, three different components, your x component, y component, and z component, or I, j, and k are unit vectors. So it could be your position vector is, x times unit vector I and y times unit vector j. And we've have t in parentheses here because x, y, and z are going to be functions of time, right? They can change with time. And displacement is, the change in your position. So your position at time 2 minus your position at time 1 would be an example of delta r there. And as we know, velocity is going to be the derivative of your position with respect to time. And so if you think about that, it's going to be a derivative, d dt of the full expansion of your position. And how does that work? It basically just distributes in. So your velocity with respect to time is just going to be your the derivative of your x position with time times this unit vector, and your derivative of your y position with time times this unit vector, and the derivative of your z component times that unit vector there. And so we can write it out as our velocity is the magnitude vx, our velocity in the x direction times I, our velocity in the y direction times unit vector j, and our velocity in the z direction times unit vector k. All right, so here's a very important concept which is going to make 2D motion calculations super easy. And that's this independence of motion principle. And you should read about this in your textbook, but I'll introduce it and summarize it here. And it's basically that we're able to treat motion along perpendicular axes separately from one another. So if you think about that, if you move directly up in the vertical direction, did you change your horizontal position? No, right? And if you move in the horizontal position only, did you change your vertical position? No, right? So you can treat those motions separately. And so often we'll talk about, the horizontal direction motion being unaffected by any vertical motion, and vice versa. Your vertical motion is unaffected by any horizontal motion. And if you have a z-axis, moving along the z-axis is not going to affect your position along the x and y-axis. And that's pretty intuitive, right? So it makes for some simple results. So for example, if you have two baseballs that, let's say they're initially in the exact same position, and then you drop each of them, one of them has a zero velocity component, so it's just being dropped straight down. The other one is thrown with a velocity vx naught, so that's like the initial x velocity. And it's going to be the velocity throughout because we're going to say there isn't any acceleration in the x direction. However, they both are accelerating down from gravity in the y direction. So if you look, this is a snapshot of the blue ball is the stationary one, and the black one is the one that's moving, let's say 1 meters per second to the right initially. You can see that they get further and further apart at different times, but their vertical position at each time stays at the exact same level, right? Because they're accelerating in the vertical direction at the exact same rate. The only thing that's changing is their horizontal distance apart. All right, so the horizontal distance can be described as the horizontal velocity of the second ball times time, right? That's going to give you the distance that those two balls are apart. Yeah, and the important thing being, right, independence of motion. Yeah, obviously, if I had given you a problem like, let's say the balls aren't falling and this ball is moving to the right, can you give me the distance between the two balls after a certain amount of time if I told you the velocity? You'd say no problem. And now, if we do this new problem, let's say the same thing. One's moving to the right, the other isn't, but now they're both falling. Can you give me the distance between them? Well, it turns out to be the exact same answer, right? Because their vertical velocity is not affecting the horizontal velocity at all. All right, so similarly to how we defined, velocity in 2D, acceleration in 2D is similar. Remember how acceleration is the time derivative of velocity. So it's like taking the time derivative of each individual component of the velocity. And this will give you, for instance, we might call this AX, A subscript X. And we might call this the derivative of the y velocity component, A subscript Y. And if we're doing a three-dimensional problem, which will be pretty rare, we would say the acceleration in the that direction would be A subscript Z. All right, so let's look at, and I'll go ahead and work this from scratch, a 2D example that's going to be fairly simple. So similar to what we talked about up above, a ball is thrown horizontally at 3 meters per second from a 10-meter tall cliff. How far from the cliff does it land? All right. So what's the first thing we do when we encounter a word problem? We draw a picture, right? So we're going to draw a nice picture. Here's going to be our cliff. And I'll draw the ground up here. We'll draw a nice little person throwing a ball. And we'll say V naught X is 3 meters per second. And then we'll go ahead and label this. We'll label this height plus the guy H equals 10 meters. All right, and so what we want to know is how far does it travel? What's this distance d, right? And we can sketch out, maybe it's going to look something like this. All right, so the first thing to do, or sorry, the second thing to do, now that we've drawn our picture, is we want to write down what do we know about our initial position and initial velocity and our acceleration in the x and y directions. So let's write down everything we know about the x components of this problem. All right, so we know that x naught is going to be equal to 0. Let's say we define our axes, right? So we're going to say have this point, we're going to say this point is 0, 0. And that's in the positive direction, and that's in the positive direction. And what's our final position, x final? It's going to be d. We don't know what that is yet, but let's say that's d, right? That's what we're trying to find. And what's our initial velocity? Our initial velocity is 3 meters per second, like we said. And then what's our acceleration in the x direction? it's going to be 0. We didn't specify any acceleration in this free fall problem in the x direction, so it's going to be 0. And now we can write down everything we know about the y components. So what's our initial y position? y0. We're still on top of the cliff, right? So y0 is going to be 10 meters. And what's our final y position? Oh, sorry. When we hit the ground, right? So we're going to be at 0 meters elevation. And what's our initial y velocity? Vy naught. It's going to be 0. And what is our acceleration? There we go. Our acceleration is going to be negative g, so negative 9.81 meters per second squared. All right, now that we have these, we want to think about, okay, let's maybe write down some of our kinematic equations. So we'll write down our kinematic equations. Let's write down the kinematic equation for the y position. We'll say y final is going to be equal to y naught plus velocity in the y direction times time plus 1/2 acceleration times t squared. Acceleration in the y direction times t squared. All right. So we said that our initial velocity in the y direction is 0, so that's going to simplify. And then let's fill in the other numbers that we know. Our final position is 0 meters. We're on the ground at the final position. Our initial position is 10 meters. And then this is acceleration in the y direction is negative 9.81. So it'll be minus, and let's just say to simplify things, we'll just call it 9.8 instead of 9.81. 1/2 of 9.8 is 4.9, so minus 4.9 time squared. So I guess the big question that we're seeing is, what's this variable t? That's how much time it takes to get to the ground. And as you can see here, we have an equation, and then we only have one unknown. So we have one equation, one unknown, which means we can solve for this unknown. That's right, so we just simplify it by getting t on one side by itself. So we have negative 10 meters equals negative 4.9 meters per second squared times t squared. So the negative signs will cancel out when we subtract over. T squared is going to be 10 over 4.9. And then where this is meters divided by meters per second squared. So what's that going to turn into? That'll turn into 2.05 seconds squared. So t is going to be equal to the square root of 2.05 seconds squared, which is going to be around 1.4-ish seconds. I don't have my calculator on me, so we'll say that. Okay, so we've solved for the time that the ball is traveling through the air. So let's circle that. We've solved for the time that it takes for the ball to hit the ground. Now what we want to know is that distance d. How far away did it land? All right, so let's pull up another page here and write down our kinematic equation in the x direction. So x final is going to be equal to x naught plus v naught x times time plus 1/2 ax, acceleration in the x direction, times time squared. So you can see that this is going to get pretty simple because in our problem, ax is equal to 0, right? So this term is going to cancel out. And our final x position, we called that variable d, right? Our initial x position was 0. And this is v naught x, which we said was 3 meters per second times time. And good thing we just solved for time. If we had tried this, the x equation by itself, we would have ran into, oh wait, how much time is the ball moving? We wouldn't have known that. But luckily we've solved for that now. So we can say d is going to be equal to 3 meters per second times around 1.4 seconds. So it's going to be around 4.3 meters. Okay, so as you can see, we use the independence of motion to our advantage because we if I had just simply said, what if the horizontal velocity is 0 and you just drop the ball, how long does it take to reach the bottom? It would still be the same answer, right? As long as it's being dropped from the same height and we're on the same planet with the same gravitational pull, it would take the same amount of time. And then we're able to use the time that we calculated from how long it's falling to figure out how long it's also moving horizontally before it hits the ground. All right, so that's a nice worked example of taking advantage of the independence of motion to solve these 2D problems. All right, thanks. See you in class.